In this video, we're going to do an example of a Lewis structure for a polyatomic ion, and this Lewis structure is also going to touch upon the concept of resonance structures, which are sometimes applicable in some of our molecules that we're drawing or polyatomic ions that we're drawing. So we'll do the example of carbonate. We'll do CO3, which has a charge of -2. And so when we're doing that, we're going to calculate the number of valence electrons. So for carbon, it's 4 valence electrons for carbon. For oxygen, we have 6, but don't forget there's 3, so it's 18 valence electrons. And then when you add them together, you'll get 22 valence electrons. But don't forget you have a charge over here of -2, and so you do have to add 2 more electrons to your total to get 24 valence electrons for the entire structure. If that was a -1, you would have added 1 only. If it was -3, you would have added 3. And if it was positive, you would have taken away electrons instead. So now the rest of the steps are essentially the same. We're going to draw the central atom, so carbon. We're going to place some oxygens around it, and we're going to connect them by single bonds over here. And when we do that, that means we've placed 6 electrons. We have 18 left to place. And so we're going to place our 18 until they're all happy there. So that oxygen's happy. This one is now happy. This one is happy. And so far we've placed 18. And you'll notice that carbon is not happy. It only has 6. And it's not one of those ones that can be incomplete. It has to be complete. It can't be more than complete because it's in period 2. So it's got to be just complete. So we're not gonna go overboard there. So we're just gonna ask one of the oxygens to help us out with some bonding. So this oxygen will say, "Yep, I'll give you that bond there." So we'll go ahead and redraw that like this. And then 1, 2, 3, 4. And now everything's happy, and we can put a little bracket around it like this and put our -2 above here. Now, the thing a lot of students ask is they say, well, how come the other oxygen couldn't have given the electrons to the bond? And that's a possibility. Instead of this one, instead of the green one doing it, why don't we just do this instead? So could we have gotten this structure instead? And so if we did that instead, yours would have looked something like this. So we'll put our square brackets, our carbon, our oxygen here contributed, and these ones did not contribute. Then we have our -2 there. And then another student might say, well, okay, how come those, that oxygen can help, but why didn't the one on the left help? Could that one have done it instead? And yes, the answer is yes, that one could have done it instead. So you could have had this instead here, and your structure would have looked like this. With the other two not contributing. And so what this actually illustrates is that these are equivalent structures. So all these structures are equivalent. They're not really any different from each other other than the electrons sort of being in different places. So the structures are equivalent to each other. They're just differing in the electron pairs being in different places. But the atoms are still in the same place and connected the same way. So the carbon and oxygens are connected the same way in the same relative locations. It's just that the electron pairs are in different locations. So we have one here versus here versus here. They're all equivalent. So you might ask, well, which one's the best structure to draw? And again, because they're equivalent, there's no best. In reality, if you were to do some experiments with this, you would find that the structure is actually a hybrid of all these. It's like mixing paint almost, right? So if you mix different colors of paint, you have a different color that comes out that's a hybrid of the two colors. And so this is what's happened here. In cases like this, where you can have a choice as to where you put your double bond, as long as the atoms remain the same and everything looks equivalent, these are called resonance structures. And to illustrate resonance structure, what we do is we put these 2 arrows, we put this arrow like this with the 2 arrowheads. And that shows that they're simply equivalent structures, and the entire structure of this carbonate ion is actually a hybrid of of all these resonance structures here. So in some cases, you're able to choose. Like you can say, well, this one can contribute, so can that one, so can that one. So in those cases there where you can choose, you should draw all the structures out, all the possibilities out, and then put these arrows to indicate that you have resonance happening. Again, they're not separate, distinct substances. The real sort of structure is a hybrid of all of these, but we draw all three to show that resonance is a possibility in situations like this here. So that's an example of a resonance structure occurring. And we've drawn a polyatomic ion of carbonate in this situation here. Another example that I'd like you to try out so you can check out in the next video is the ozone example. And then we'll try a few more polyatomic ions in the next video as well. But for now, make sure that you're able to do a variety of different Lewis structures, including polyatomic ions, and be able to show and explain resonance in structures where that's possible. So again, they need to be equivalent structures. Here, the electron, the double bond is just in different regions, different between different atoms. CNO up here, CNO over here, CNO over here, but they're all bonded in the same relative order. So there's nothing different other than that placement of that double bond for it to be considered resonance.